Good evening, everybody. Today we'll just go for some more examples of those solid state compounds what we are talking about, that means the spinels. Some remaining examples of these spinels and what are the experimental evidences we can have So, experimental evidences for basically the typical crystal field splitting. That means whenever a metal center is present and if it can have some immediate environments either tetrahedral or octahedral, and when we talk about these spinels, we can have these oxide anions, and today we will see also the sulfide anions. So, these are the corresponding ligands, either oxide or sulfide, surrounding the metal ion in a typical tetrahedral geometry or an octahedral geometry. So, whether we can have the corresponding crystal field stabilization and as a result whether we can calculate out the corresponding CFAC values for these systems depending upon the different dn electron configuration. So, they can have different dn electron configurations, and based on that we can have the preferential occupation of the different levels. In case of TD, we can have E level as well as the T2 level, and in case of the corresponding octahedral geometry, we can have the T2G level and the EG level. So, when we calculate out the corresponding stabilization energy, we find that the preferential site occupancy for some of these metal ions in different electronic configurations are there for a typical spinel structure where we have M2O4 type of formula, where M is the corresponding bivalent metal ion and M prime is the trivalent metal ion. So, when we put these bivalent and trivalent metal ions, what we know already that depending upon their different electronic configurations, we can have the corresponding CFAC for these electron configurations in these two geometrical forms. So, when we find that how many number of electrons, unpaired electrons are present, as we know that if it is a copper based spinel, copper 2 plus based, it can be a spinel or it can be a corresponding simple complex such as copper tetraamine complex or copper hexaco complex. So, when it is spinel, we can have the configurations for these two geometries, TD and OH geometries. So, we can have the corresponding number of unpaired electrons. Similarly, in case of complexes also, it can be a corresponding square planar complex or it can be a corresponding octahedral complex. So, all these cases will have altogether different number of unpaired electrons. So, we have different numbers of unpaired electrons to the system. So, if we have the unpaired electron, we will see that it can rotate around the positively charged nucleus, which is positive. charged. So this electron can rotate around this positively charged nucleus, and due to its spin contribution as well as its orbital contribution, it can give rise to the corresponding magnetic moment. So depending upon the number of unpaired electrons present in all this system, we should be able to calculate out theoretically as well as we can experimentally determine the corresponding effective magnetic moment of the system. When we are talking about a system where the individual unpaired electrons, if it is copper 2 plus, we know that it is a 3d9 system. So we have one unpaired electron, and that unpaired electron is responsible for giving rise to the corresponding mu effective value. So in a magnetically dilute system where this unpaired electron is getting shielded, because this unpaired electron belongs to one particular metal center, and if the copper 2 plus center is there, and we can have either the different oxide ions, sulfide ions, or the simple ligands like ammonia. So this is the corresponding geometry around the copper 2 ion in a particular complex where the individual copper centers bearing one unpaired electrons are separated. That means this molecule is separated enough to the second molecule or the third molecule and so on. So these particular unpaired electron residing on the single copper center can give rise to a typical paramagnetic center, and it can give rise to the corresponding magnetic moment value due to the presence of one unpaired electron. If they are close enough and they are nearby, then one particular unpaired electron having some moment value can interfere with that of the second electron, and they are basically coupled together, and we are able to see the corresponding magnetic interaction. And there are different types of such magnetic interactions which can control the overall magnetic moment of the system due to some other type of interactions that we will slowly discuss one after another. So regarding these spinels, what we have seen that we have earlier discussed about the typical aluminum spinels and the iron spinels, where the basic structure is made up of aluminum, and within the aluminum spinel we have the magnesium, and case of iron also the Fe2O4 system we can have, and there we have the other metal centers. Similarly, in case of these chromium spinels, and there are 3 or 4 examples. The first one is very well known due to the presence of it as a mineral system. So chromite we all know that this chromite is the typical ore for chromium. So not only it can be processed for chromium extraction, but at the same time it is present within a complex matrix of iron. So this iron matrix is present, which is the spinel matrix, and this can also be processed for iron as well. So if the system is such that we can have this chromium iron system, and if the corresponding physical technique is available such that the corresponding percentages of chromium as well as iron can be incorporated in some solid solution, which can be our chromium based alloy. So that particular physical technique can also be available, where if the corresponding percentages of chromium as well as iron present in the chromium ore matches to that of the corresponding alloy formation, then that procedure can be utilized as the chromate ore as the starting material or the raw material for the corresponding alloy formation. So like that of our typical spinel structure bearing aluminium, in this particular case also if we can have this chromite structure with that of iron is present with Cr2O4. So if this is present, so when the chromite is present, so this is Cr2O4 2 minus, and iron is present as Fe2 plus. So this also we can have both iron and chromium, and these iron and chromium can be utilized for in a similar fashion for the corresponding alloy formation. So next we see that how within this all chromium based spinels we can have other metal ions such as magnesium or zinc. So when magnesium is present we get the magnesiochromite, because the basic infrastructure for this network is based on chromium and oxygen. So the network bonding is formed with chromium and oxygen. That means we have the corresponding oxide lattice, and depending upon its normal or inverse spinel structure, we can have the entire or the all chromium atoms sitting comfortably within the octahedral sites, or in the inverse structure some of them goes to the tetrahedral sites. Similarly, in case of zincochromite, the zinc is present along with the chromium network, chromium oxygen network. And also we can have the copper present in that particular spinel structure, and we have the corresponding compound as copper Cr2O4. Thus we know that depending upon the nature of the spinels, the network is forming either from aluminum to giving aluminum spinel, then for iron spinel, and for chromium we get the corresponding chromium spinels. This is one such thing. That means this is the figure typical for the chromite ore what we can get from underground for due to excavation for the chromite ore. So this can be processed further for utilizing it as mineral. So this looks like a shiny mineral like structure. So when iron and chromium mixed oxides we can have, it can be utilized for some catalytic reactions. So at high temperature, this particular compound, this raw material, which can also be synthesized artificially in the laboratory, we can prepare this chromite type of material having different texture, different physical morphology, and different network or the corresponding powder structures are different compared to that we get from the native environment as the ore, and this can be utilized for a catalyst, and the catalytic reaction is only operating at high temperature. So one such important example of chromite, use of chromite for water gas shift reaction, where carbon monoxide is reacting with water vapor. So how carbon monoxide could be utilized to react with water vapor for giving us the corresponding carbon dioxide and hydrogen, which is basically the mixture what we get is known as water gas. So the corresponding water gas shift reaction can show some catalytic activity due to the presence of either chromite or some synthetically prepared, which we can prepare in the laboratory for this sort of material for its catalytic behavior. So when carbon monoxide is coming, it can quickly interact with the chromium center, because we all know that chromium obviously in its native form, that means in its elemental state, that means in the zero oxidation state, can react with several such carbon monoxide molecule, and when it is reacting in the zero oxidation state, it is giving chromium hexacarbonyl. So this hexacarbonyl formation gives us some important clue that this chromium center, whether it is in the +2 or +3 oxidation state or the 0 oxidation state, can show some interaction with the carbon monoxide molecule. So, the surface of this chromium, so this chromium surface, so chromium surface can show some affinity for its interaction to the carbon monoxide molecule. So, surface shows some affinity to interact with the carbon monoxide molecules. So, they are showing some kind of interaction, and this interaction is taking place, and we can see that the corresponding water gas shift reaction we can have. So, if this carbon monoxide molecule can react with the chromium center, giving rise to some kind of interaction on the chromium surface, because this iron present, if it is present in the surface, this iron can also show some interaction with the carbon monoxide molecule, because these iron pentacarbonyl type of molecules are also very much stable and well known. So, apart from these interactions for the formation of the hexacarbonyl or the iron pentacarbonyl, we see that carbon monoxide has some good affinity to react with any of these two metal centers. So, as a result, we get a mixture of these two gases when the vapor of water molecules are reacting with carbon monoxide gas, giving rise to the carbon dioxide as well as the hydrogen gas. This is one of the useful technique for utilizing this water gas shift reaction to eliminate the carbon monoxide burden in our atmosphere from automobile exhaust, or in some other cases for environmental point of view, we can take care of these carbon monoxide molecules, and we have plenty of these water vapors available we can produce in the laboratory also, such that we are able to produce a good fuel gas, which is our hydrogen gas. So, hydrogen gas production can be a very useful technique utilizing these spinel based catalysts. There are some other type of these catalysts can also be utilized for different types of organic transformations at the same time. So, how we can increase the corresponding catalytic function or the catalytic behavior of this spinel type of molecules? If we go for simply changing this metal center, that means this iron center, by some other catalytically more active or catalytically efficient metal center like that of copper. So, one such example is that is not typically a corresponding copper chromite formulation like CuCr2O4, but it has something more. So, is a mixed oxide structure where we can have copper chromite, copper oxide and barium chromate. So, both chromate chromite form is present over there, and this chromate chromite form is coexisting together in the solid state. So, in the solid state structure we have the corresponding formulations for copper chromite, copper oxide and barium chromate. And in organic chemistry, for typical organic chemistry synthesis, we find that this catalyst is very useful for hydrogenation reactions. So, there are some more of these type of spinel molecules which are available for such hydrogenation reactions, including the corresponding hydrogenation reactions followed by ring opening reactions. And such reactions are very much useful in organic synthesis, and people are still working on it to develop new and newer type of such catalysts based on these spinel structures. So, how we can make this copper chromite formulation if it is not available in the native form in nature as a mineral or some ore, we can prepare this particular material for a solution state synthesis in the laboratory or in some point to get some beautiful crystalline form or particular size or particular some nanoparticle type of molecules we can have. We get these as a typical precursor and then corresponding treatment, the heat treatment or something else, utilized for the corresponding hydrothermal synthesis. So, in solvent, if the solvent is a typical water, we mix off the individual ingredients, that means the corresponding salts which we require for the synthesis of this copper chromite, including the barium. That means some amount of barium salt, some amount of copper salt and some amount of chromite salt can be utilized. So, we have the precipitation which can be filtered out we get the residue as a solid product. We dry it and then we heat it at a particular temperature, heated at say about 400 or 500 degrees centigrade, giving the useful catalyst. So, these are the very simple technique for solution process for the preparation of new and other type of catalyst. So, in this particular case, how we make this barium chromate based copper chromite catalyst is that if we take the solutions of barium nitrate and copper nitrate and a mixture of these two can be added to another solution of ammonium chromate, results in a precipitate which is of different formulations. Say barium nitrate can react to give with ammonium chromate, giving rise to barium chromate, and copper nitrate is also reacting with ammonium chromate, giving rise to some copper chromate formulation, and ammonium ion is there and ammonium nitrate is there basically. So, the presence of ammonium nitrate in the medium basically responsible for the reduction of the precipitated copper chromate at high temperature, say not at 500 degrees centigrade but less than that, which is in the range of 350 to 400 degrees centigrade. So, at this particular temperature, the ammonium nitrate which is present over there will be responsible for the reduction of copper chromate to copper chromite. So, is basically some mixed oxides are formed like that of our typical examples what we know for different superconducting oxides, which are also different mixed oxides of say perovskite or any other type of solid state structure. So, these mixed oxides of superconducting type can be formed and it can only result at a particular calcination temperature, because the precipitate, the dried precipitate can be heated at a 350 to 400 degrees centigrade for the typical calcination reaction. So, this can also give us some other example of the ruby. So, the naturally occurring ruby material is nothing but is a corundum crystal based on alumina, based on alpha alumina sometimes, that is being doped with some chromium 3 ions, and when chromium 3 ion is doped within the alumina crystal lattice, we see the chromium is occupying some of the holes or the equivalent sites in this particular alumina structure, and the chromium oxygen bonds are getting lengthened, and the chromium in some octahedral environment giving rise to the corresponding characteristic coloration due to the corresponding shape which is determined by the corresponding structure of the corundum. So that basically gives us whether we have some elongated chromium oxygen bond or compressed chromium oxygen bond, and that is responsible for the corresponding DD transitions based on the chromium in +3 oxidation state. And this particular color is not always available, the red color, which is not available all the time, but due to this particular presence of this chromium we can have some other colors also, and these corundum based gems can also be termed as sapphires if the colors are different from the red color of the ruby. So a red colored artificial ruby may also be achieved by doping chromium 3 into artificial corundum crystals. So in the laboratory, if the available corundum is not naturally occurring, we can dope artificially chromium 3 into the artificially prepared corundum crystals, and thus we are able to make the corresponding ruby, which can be prepared in the laboratory in a synthetic way, and we call them as the typical procedure for the production of synthetic rubies, because synthetic rubies are very much useful for different optical instruments and for optical properties. So one such synthetic ruby crystal can be utilized for the generation of laser, which is nothing but light amplification by simulated emission of radiation. So this laser is basically dependent on the ruby crystals, and these are known as ruby lasers, and it's basically dependent on the stimulated emission. This S is stimulated. S is the stimulated emission of light from the chromium atoms in such a crystal when chromium is trapped within the corundum lattice, and this chromium is responsible for its red coloration due to the typical crystal field which is being exerted on the chromium center in its +3 oxidation state. So we get the corresponding ruby lasers. So ruby lasers, its red color is due to the corresponding crystal field stabilization energy within the corresponding crystal lattices of the corundum system. Next, we will see some molecules which belong to the thiospinel group. So whenever we see that the corresponding magnetite or hematite molecules, we see that there are several such spinel molecules are available where 3 manganese, 3 cobalt or 3 iron centers are there within the O4 oxide lattice structures. So these structures are there, and all these molecules or systems can have a very strong MO bond, and the nature of this MO bond is it is ionic type. So all the color and all other things can be very well explained in terms of the corresponding crystal field, which we can have, which we can exert on the corresponding metal center due to the presence of these oxides. Now if we move from these oxide anions to some sulfide anions, because we know that large number of sulfide based ores and minerals are available in nature.